Okay, so we will start at 5 p.m. on the dot, but I just want to make sure the technical issues have been sorted and everything is working as it is intended to. I should be able to see the chat, or if anyone wants to comment, they can comment via the chat. Let me just check that because I have 3 minutes, so I will go about checking it. Great, I can see that. That's all good. We'll start at 5. So before we really get started on, I guess, the content of what I'm going to cover this week, I wanted to kind of make a little bit of a note as to why I chose this particular platform, why I'm covering everything on Twitch, why I'm not covering everything live, obviously, from SIT, and how we're going to run this over the course of the next 4 weeks and until mid-semester break, and hopefully the entire semester, if we can manage it. So, when the coronavirus came around, we didn't really have a plan in place for taking these programming competition lectures and these workshops and things, and these training sessions, and somehow putting them online. We didn't really have a big plan of how to do that. And then we eventually managed to figure out things. Syncs managed to put a number of its other events online. For example, the hackathon and many other things. The trivia nights. A lot of the Syncs events were going online, so we figured, why not put the ProgComp, the programming competition workshops online too? So we managed to do it. I think that Twitch is probably the best platform for doing it, mainly because I have experience with it. I was going to do Zoom and have a little bit more interaction, but I thought, okay, Zoom is very clunky. The writing will be quite annoying. Like writing math and writing words and things will be just slow, and there might be a lot of lag. And yeah, I think that Twitch has kind of perfected the technique of being able to stream live with high quality and at the right time. So yeah, I think Twitch managed to perfect it in the last year or so. So I decided I was going to do a number of streams on Twitch to try it out, which I did, and then now, well, I have some experience with it now, so hopefully we should have no technical problems with all of our things going on. I hope everyone can hear me. I hope the technical issues are totally ironed out and the audio is working fine. So we're gonna get started. My name is Vinay Kumar. I'm currently an honors student in applied mathematics. I did my majors in maths and computer science. I've just started my honors. And we are going to be learning about programming competitions. So let's kind of get started. So here's how things are going to work. So we're going to be streaming 5 p.m. on Mondays on twitch.tv/VinayK24, at least in weeks 3 to 6, and maybe even longer. Hopefully we can do this throughout the semester. I'd like for that to happen. I'd really like to keep doing these streams, keep doing these workshops every Monday. I think these are pretty valuable, and I hope that we can take what was a very whiteboard based and kind of sitting around a table doing some stuff and explaining some things together, set up into the online format, and I hope that this is going to work. What we'd also like to do is a Syncs programming contest in the mid-semester break. I'll have to confirm that with the Syncs president and the rest of the Syncs executive as to how that's going to work and how we're going to organize it. But I think it should be fine. The contest will probably be held on HackerRank. Other universities have managed to pull this off, for example, UNSW and things like that. So I think we can pull it off. Some resources. So I'm going to be closely following a set of 9 notes that I have put on the Syncs Discord page. I will actually just quickly travel there just to show you, just to kind of show you where they are. One moment. So I can travel to the Discord page. So we have Syncs Discord here. And inside Syncs Discord, there's a topic of ProgComp. And inside the ProgComp, I've posted a number of things, but mainly 10 sets of notes, each of which is about 5 pages long, not too long. But they're right over here. Essentially going through a number of topics that we're going to learn. I'll be following these kind of notes fairly carefully, so we'll see how we go. But yeah, in terms of resources, these notes are going to be pretty similar to what I'm going to cover. Obviously, there will be some differences because I want to make things a little bit more interesting. But yeah, for the most part, for alternative exercises, for other things you want to do, this is where you can find things. Especially for people who are new to the subject. For people who are experienced, then well, you have your own like training and things to do, and you can really decide what you want to do. So let's get back. Okay. So other resources that are available. I highly recommend things like the Sphere Online Judge, USACO, ORAC. These are all programming contest platforms, and Google's training site. They're all very good for learning programming contests and for practicing your skills. And I think that these are really great to learn from. Okay, in terms of opportunities to really practice and do contests. So first of all, there will be the Syncs programming event in the mid-semester break. There will also be, for example, Google Kickstart contests throughout the year, which is easy to find. I of course will be putting the notes, the PowerPoint, the entire video will be up on YouTube. The presentation will be up on the Discord page. Everything will be available for you. So yeah, Google Kickstart throughout the year. Code Jam is another programming contest which runs from April to June. There's ANZAC programming contests, which are essentially collegiate or university programming contests where you can represent the university. And they are, well, the first one is next Saturday, September the 12th. Then there's one on October the 12th and October the 17th, 2 contests then. And October the 17th being particularly important because it is the ICPC, or International Collegiate Programming Contest Regional Final. That means it's really important. And if you want to represent USyd, you should contact Dr. Legion Chang. He is the staff representative for programming contests. He runs programming contests as a staff member. So contact him if you want to represent the university, because it's a big opportunity. It's a really good chance for you to improve your skills. Okay, so let's get started with the actual content of what we're going to do today. So why are programming contests important? So first of all, they kind of teach us how to use our programming technique, how to practice them, put them into practice on real world problems, and how to use content from your second year courses, for example, data structures and algorithms, how to put that theory into practice and use it on use it on more real-world and practical style problems. The second reason is a little bit more complicated. The world is kind of stuffed with these insanely hard problems that require a lot of data processing and ways to intelligently process a lot of data. So often, extracting insights from data, like data science, is full of this, trying to figure out not just ways to just run through data, but also to process it very smartly, to arrive at intelligent insights from it, to understand what is really going on. Theoretical computer science is, of course, beset by this, because the entire fields of things like algorithms and theoretical computer science is really about this, trying to figure out ways to scale things so you can tackle problems so that you can tackle problems at scale, and also finding more intelligent ways to do things that we do know how to do, but not necessarily very efficiently. So yeah, theoretical computer science is all about this. Practical computer science is also about this, right? For example, you see this in data science in the real world with organizations like Facebook, Google, and Amazon, essentially trying to hire people who are not just programmers, but also have this knowledge of how to make things work at scale. How do you intelligently process data so you can unpack information and answer certain questions? So the hard part of programming contests isn't necessarily the actual coding and the programming, but it's the logic and the insight behind it. Okay, but what do you actually do in a programming contest? So the problems are algorithmic in nature, so you need to solve them using a computer program. Essentially, you're given some input, your computer has to process this input, and you need to produce some sort of output. In addition, the programs have to be correct and efficient. So what I mean by correct is that for any given input, they need to produce good answers, or correct output. So for example, the correct output might be the right answer to a particular problem, the best answer to a particular problem, some sort of optimal solution, maybe some sort of feasible solution to some sort of problem. For example, here's a simple problem, right? Let's say you have some Sudoku puzzle and you want to solve it. So a correct solution would be essentially a filling of these numbers in the grid, so that all of the rows only contain a single number contain all the numbers from 1 to 9, and no two in a single row. The same with the columns, and the same with the boxes, right? So that's the specific criteria for correctness, and your programs have to satisfy that. The second criterion that your programs have to satisfy in a programming competition is efficiency. So this is where the kind of insight comes into programming competitions, and why programming competitions just teach general problem-solving skills that are specifically really important and are kind of prized by big tech companies, research, and other areas too. The reason is that often a solution is kind of useless if it's not necessarily very efficient. So for example, let's say I make a startup and I build a website. My website can handle 10 people with a few servers and things. With my bought $30 server, I might be able to handle 1,000 people at once. Can I handle 10,000, 100,000, a million? Probably not, right? I have to do some sort of scaling to handle that. So I have to be more efficient with the way I'm processing my data. I have to be more efficient with how I store all of that data, how I use it, and of course my entire network infrastructure and all of that. So there's a lot of efficiency bottlenecks. So solutions can be good, they can be correct, but they may not be efficient. And that kind of reduces their value. So in a programming contest, they evaluate this by essentially running your code on test cases. And here's where we come to kind of a little bit of Zoom knowledge. So I'm hoping you guys are familiar with the material from Introduction to Programming, maybe in your first year semester 1 courses. And you might have seen these automated judges where the judge runs your program on a bunch of test cases. It spits out whether it's right or wrong, and it gives you a mark. The principle is the same here. So what happens is that when you've finished your program, you submit it to an online judge. What it does is it tests against a large number of test cases. Maybe it's 50, maybe it's 100, maybe it's 200. And essentially, it tests whether the program gets the right answers and whether it actually gets the right answers in a specific amount of time, which is essentially used as a measure of efficiency. See? So, yeah, you need to not just get all of the answers correctly, but also do it in a certain amount of time. Otherwise, your program will be timed out. So there's a time constraint on your program. So what does a programming competition problem look like? I mean, it might just be easier. It might just be easier to just show you, but I'm going to tell you and then I'm going to show you. So, okay. So the first thing that will be specified is kind of the input and the output. So how are you going to read the answers? Read the inputs, and how are you going to display the answers? So what are you going to take in? What are you going to take out? How are you going to take it in and out? The second part of the problem will be the time limit. So it will tell you either at the beginning of the problem or at the end of the problem how long your program has to take to pass each of the test cases or pass all of the test cases. You'll then have what's called the flavor text. The flavor text is kind of a description of the problem in a way that is easy to understand. It might be in the context of some sort of real-world application. It might be just an absurd fictional scenario that makes no sense, but is quite fun to read about. It's meant to kind of ease you into the problem and make you understand what the problem is trying to get at, what they want you to do, without necessarily intimidating you, and without essentially giving you the entire technical formulation all at once. They want to kind of motivate the idea. You'll then have an input description, which is just like what you need to get in as data, what you need to output, and a sample test case to help you out. So they might give, okay, here's an example of what we want. This is the example output that you should produce. And maybe some subtasks, like if you want some partial marks, here's something you could do that will not get you full marks, but will get you some marks. And it will probably be easier than the entire problem. Okay, so now that we've done that, let me actually show you what a problem looks like. Okay, so here is an example. Here is an example of a problem. Okay? Very simple problem, beginner's problem from an Australian site. Very, very straightforward, this one. Okay, here we go. Let's have a read through it. So first we have obviously the problem title, drought in this case. We have an input and an output file. So what that means is that we are going to be reading information from this file, rainin.txt, and our program is going to be writing to another file, which is rainout.txt. And yeah, we have to output and input that information. So our program needs to take in these names and input information from that file and output information from the other file. To the other file. Now we've got the time limit, right? We see kind of the structure permeating the problem. So the time limit is 1 second, meaning that for any given input scenario, for example, sample input 1 over here, our program needs to be able to find the answers within 1 second. Now we've got the flavor text right over here. Let's have a read of it. Years of drought have hit rural Australia hard. With catchment levels at an all-time low, few decide to purchase a rainwater tank. Soon the winter will arrive, the winter rains arrive, and the tank slowly begins to fill. You begin to wonder when your tank will be entirely full. A friend at the Weather Bureau has kindly lent you rainfall predictions for the next few days. Given these predictions and the size of your rainwater tank, write a program to determine how many days your tank takes to fill. Obviously, this is not a particularly difficult problem. It's not too insightful, but it's meant to illustrate what the process of solving a programming competition problem is like, what the ideas are like, and how you go about it. Okay, so now we have the input. So that corresponds to step 4 here. Number 4, the input description. So here we go. The first line of the input file will be of the form n. So n is the number of days the weather prediction lasts. C is the capacity of your rainwater tank in liters. So here we go. 6 and 10. Can you see the first line of the sample input? Really simple. 6 and 10 means, okay, we have 6 days. The weather predictions last 6 days. As you can see, there's 6 numbers here, 4, 5, and 6. Right? 6 numbers here, which means that the predictions last for 6 days, and they tell you that. And the capacity of your rainwater tank in liters is 10. Okay. So you're given this. You are guaranteed that 1 is less than or equal to n is less than or equal to 1,000, which means that essentially the number of days the weather predictions last is less than or equal to 1,000. And C is the capacity of your rainwater tank in liters. Okay, we've said that. C is a positive integer no greater than the total amount of rain that falls over the n days. Okay, so essentially, if you have some amount of rain that's falling over all of the days, that the capacity of the rainwater tank has to be smaller than that, essentially. The remaining lines of input will describe the rainfall levels for each day. So for example, on day 1 we have 2 liters, day 2 we have 3 liters, and so forth. So the input is usually fairly easy to interpret because this line input, or this paragraph, will usually tell you what the input is meant to be and what everything represents. So you should be able to look at any input scenario and figure it out. Okay, now we look at the output. Your output should consist of a single integer, the number of days until your rainwater tank fills. Alright, so for example, in this case the answer is 4. Why is that? Okay, so we have 10 liters in our tank. We get 2 liters, we get 2 plus 3 is 5 liters, 8 liters, 10 liters. So after 4 days we have exactly 10 liters, and then after 5 days we have 12 liters. So after 4 days we have filled our entire tank. Okay, let's look at the second scenario. Same numbers, except we now have a capacity of 11. So 2 plus 3 is 5, plus 3 is 8, plus 2 is 10. And then after 5 days we get to 12, which is bigger than or equal to 11. So essentially it takes 5 days to fill the rainwater tank. And then there's an explanation here. It tells you it takes a running count of all the rainfall totals, and it says hence a 10-liter water tank is full after 4 days. The 11-liter water tank is full after 5 days. Okay, great. So now let's go through the process of actually trying to program something like this. So I've already coded a solution like this in a long time ago, but we're going to code it again just for fun. Okay, so hopefully you guys can see my Python screen. Let me know if you guys can. I think it should be working fine. Do you guys want the screen to be adjusted? I'll try and do that. I'll try and adjust the screen a little bit. Hang on. Yeah, let me know if you can't see something. Okay, so the first thing we're going to do is read all of these things from a file. Okay, so we want to read from this file rainin.txt. So one idea is actually just to create a new file. So what I'm going to do is, you guys can't see this yet, but I'm going to create new files and call them, for example, rainin.txt and rainout.txt as my sample input and output files. This is easy to do and it helps with the testing process. So I'm just creating a file. I'm calling it rainout.txt, and that's going to be my output file, so where I write the answer to. Okay, I will use print statements and things for testing as well. Alright, so what I'm going to do is first let's paste the sample data. Let me go back to the other screen. Here we go. Hopefully that magically does it. Good. Okay, my Twitch skills are getting a little bit better. Okay, so what I'm going to do is I'm going to paste the sample input into my files. So what I've done here is I've pasted my input into the files. Okay, now I can start programming. All right, so the first thing I'm going to do is I'm going to define my input file. Okay, so this is my input file. So now I should be able to take the information in. So what do I need to take it on the first line? Well, the first thing I've got to do is take in these two numbers, which are N and C, the number of days the weather predictions last, and the capacity of my rainwater tank in liters. Okay, so there's a convenient way of doing this. So what we can do is we can write N C equals map int input dot split. Hopefully this is coming up in real time. I hope everyone can see this. Anyway, so now we have this N and C. So let's print this out. Print N and C. I will try and get the windows sorted. Yep, okay, that's fine. So, yeah, what we'll then do is we are going to then get all of the rest of the data. So something like for I range N, we should collect the data. So let's make some variable, rainfall today is equal to int input file. Oh, in this case, not input. What we want is input file dot read line. Cool. Okay, so we now have these numbers. And what we want to do is we want to store how much rainfall has happened so far. So let's make a variable, total rainfall is 0. This is pretty simple programming stuff. We're going to get to the harder stuff in a few weeks' time. So we have our total rainfall is 0. What we're going to do is we're going to increment. We're going to say total rainfall plus equals, or we can, just to make it even clearer, total rainfall plus the rainfall today, right? And if our total rainfall is bigger than or equal to C, so what we know is C is the capacity of our tank, N is the number of days of rainfall. If our total rainfall is bigger than or equal to C, then what we're going to do is, well, we've already exceeded it. So what we should do is we should keep a count. Let's make days be 0. So what do we need to do when we get to C? Okay? How do we deal with it? So what we need to do is we need to actually stop after that. So we should always increment our days variable until we get there. So for example, on the sample input is like 2, 3, 3, 2, 2, 4. So for the first time, when we get to 2, 2 is less than 10, so we should increment, right? And then whenever we don't satisfy the condition, we should increment, and whenever we do, we should just stop, right? So for example, if we go, oh, actually no, we should increment until we do it, and then we should stop. So we should always increment, and then if we're greater than or equal to C, then we should just stop. So for example, what we're going to do is we're going to say, here we go, days equals days plus 1. I'm not using too many shortcuts and things, just to make things absolutely clear. If the total rainfall is bigger than or equal to C, we simply break. Okay, so why do we break? We break because we now have enough days and we've managed to exceed the total. All right, so what we're going to do is we're going to print days. So for the first example, you guys don't see this, but you can actually put this in your IDEs and things. You'll get 4, and the answer is 4. So what we're now going to do is, let me drag back to the window. Hang on, let me just adjust a little bit. Window capture. There we go. So what we're going to do now is we're going to paste our sample input 2 into the file. So we're going to paste that into rainin.txt. And now what we're going to do is we're going to run the program on both sample input files. Fair enough. So let's just run, and we'll see what we get for the second input file. We do get 5. All right. So, have we finished the task yet? Well, we haven't, right? Because we haven't looked at the output format. Okay, so what's the output format? Your output should consist of a single integer, the number of days until your rainwater tank fills. Well, we have days, we've done the task, but we haven't outputted it to the correct file, which is rainout.txt. So this shows the importance of making sure that you conform to the particular specifications of the task. This is just showing you what a particular problem looks like, what are the formats of these things, and what exactly you have to do in these sorts of contests. You'll always see things like, okay, how does the input come in? It could be standard input like input and print. It could be a file, like in this case. I've used a file as an example just because it's a little more complicated. You have a bit more work to do, and you need to look at the output specifications. You should always look at the sample inputs. So before you submit, you should always try and test your things on the sample inputs. And you should also test on other particular cases too. So what we're going to do is let's first write the answer to a file. So what we're going to do is we'll write output file. Oh, hang on. Let me get back to Python. Cool, that should do it. So output file is open rainout.txt w. You could do this in a number of ways. This is the simplest. You could have used with open. You could have used anything else. What we're going to do is we're going to do output file dot write. And what do we need to write? Well, we basically need to write a string of days. And finally, we should close our input and output files. So just to be very sure. Okay, so now what we should do is we should run our particular example on another test case, right? Something that's not the sample and something that is a little bit more complicated. So one test case we might look at is something where maybe you go straight up and then you just get to the particular capacity. Well, we already had that with the 10 case. We can do another example of that. We can do an example with a very large number of days. You can do an example. You can do lots of examples, essentially. But you should try and test at least one case other than the sample inputs, because the sample inputs are usually designed to be very simple, and they're designed to essentially let you understand the problem, and they're essentially for you to be able to comprehend the scenario on a very small example. A very small and very easy example. And what you will be tested on is very difficult and very hard examples, right? Hard, difficult, and long examples. So obviously you need to be a bit more circumspect about the way you test than I will be. Okay, so I will just quickly make up a test case. For example, one idea is just to do like 1, 1, 1, 1, 1 until we get to a particular target, just to check that. Another idea is to just do a lot of values. So let me make a test case. So what my test case will be is my n will be, let's say, 5. My c will be, let's go with 5 again, because they did give a constraint over here that the number of, hang on, let me go back to the sample. They said that they did have a constraint, yeah. C is a positive integer no greater than the total amount of rain that falls, right? So we can make n equals c. See, that's an edge case that you should probably test, but that no one tells you to test, right? So you should definitely go about testing the right things. I think programming contests really teaches you how to test in a very kind of real way, in a very black box way, because you need to make sure that you get the answers right in a contest, and you don't have much time. Often you need to solve maybe 4 of these problems or more, which are much more difficult, in about 2 to 3 hours, which means that you don't really have too much time. You need to make sure you get it right on the first try. And when you don't, you need to test really well to see if you can find the bugs. Okay, so what we're going to do is we're going to make a test case. I'm doing this very slowly, simply because I want you guys to really understand the concept, right? And how a programming competition works. So we have, let's do 1, 1, 1, 1, 1. So we have 5 days, each day is 1, and we put it in. So what we're going to do is we put that information in the input file with exactly the specification that they want. So if you go back to the particular problem statement, we can have, for example, a sample input 3 where our numbers are going to be 5 and 5 and then 1, 1, 1, 1, 1. So we have 5 days, we have a capacity of 5, and we have all 5 ones. And this is going to take exactly 5 days, because after 5 days we'll get to 5 liters of water, and that's exactly how much it takes for the rainwater to fill. Note that we couldn't have a maximum capacity of, say, 6, because there must always be an answer to this problem. And they've guaranteed that C is a positive integer no greater than the total amount of rain that falls over the total n days. Alright, so now that we've tested it, we should have tested it, we should check whether the answers are correct. What we're going to do is we're going to submit this. So here we go. I'm going to submit the problem. So I choose my source file. My language in this case was Python. I'm going to click upload, and then I'm going to submit. We'll see how we go. Okay, we got it all right. This is great. We got 100%. And it took 0.1 seconds total. So now let's take a look at what a submission feedback actually looks like. So here we can see that there were 7 test cases for this problem. We got each one of these correct, so we got 100 on each case, and that gave us a total score of, you guessed it, 100. And it took us between 0.012 and 0.016 seconds for our program to output the answer. That makes sense, right? So if we go back to the problem statement, what actually happens is, well, n is less than or equal to 1,000, so we only had to process 1,000 numbers and just output the answer. So we only had a simple linear search to do, to go through and add things up, and it was simple enough to code up. And because we only had 1,000 data points, being able to loop through those 1,000 doesn't take very long. So here's a piece of computer wisdom. Computers take about 50 million operations, can do about 50 million operations per second. This was back in 2006 or so. Now the figure is closer to 100 million. So around about between 5 times 10 to the 7 and 10 to the 8 operations per second. So given that, with essentially 1,000 operations to do here, or maybe a couple of thousand, it wouldn't take very long. It should take, around about 0.1 of a second or less. And if I coded this up in, say, C++ or C, it would actually take a much shorter amount of time than if I used Python. But I'm coding with Python simply because I'm kind of catering to everyone. I'm assuming everyone has some knowledge of Python, or if you don't, Python looks so close to pseudocode that it won't matter anyway. Whereas if I did this in C++ or Java, I might have to get into the kind of specifics a little bit more of like particular libraries and all of that, and it'll just be a little bit more messy. So I think Python is kind of a natural way to teach this. Okay, so what we've been able to do is we've got our problem, we've submitted. Here are some comments. We got our numbers. We have our total rainfall. So what we did was we stored the total amount of rainfall. We had a count on the number of days. We added everything up. We incremented the amount of days. And if we exceeded the total amount of capacity of our tank, we just broke, which meant we stopped the loop and we just outputted the answer. Very simple, right? Not too many lines of code to actually write. But it's meant to illustrate the process of what a programming competition problem is like. Okay, so now in the last, 15 minutes, let's go into some more ideas. So of course, if you guys want me to put this put this code up, I will. Otherwise, it's not very needed, but I'm sure you guys can code this up and submit it. That's kind of homework, but it'll take less than 10 minutes to do. I took about, 15 to 20 minutes, simply because I was just explaining every little bit of the process. So it shouldn't take very long. But the point is that I want you to get used to what a programming contest looks like, what the online judge environment might look like, how it all works, and just kind of get used to it all. Okay, so let's talk a little bit about what I meant by correct and efficient. So let me comment out all of this code. Hang on, let me go back into Python. And let me comment out a lot of this code. And we're going to talk a little bit about what we mean by efficiency. So let's do that. Efficiency. Okay. So what do we mean when we say that a program is efficient, or it's not efficient, or it's fast, or it's slow? What do we mean by that? Any ideas? You guys can definitely comment in the chat. You guys can comment in the chat live, like there's an opportunity for live interaction on Twitch. So please, follow me, get a Twitch account, and you guys can comment in the chat, and I'll be seeing everything, so I can totally keep track of everything that's going on. Okay, so what do we mean by efficiency? So I want to issue the formal definitions and kind of cover the concept in a very, very broad and very intuitive manner. Okay, so in a programming contest, efficiency as you see it is measured by time in seconds. Okay? But time in seconds is a little bit weird. For example, if I ran this program on with C++, it would take a lot less time to do. If I ran this with C on a supercomputer, it would again take a lot less time. For example, you could do much more complex data sets for this problem much faster on a supercomputer than you could do on my pretty bad and trash laptop. So yeah, efficiency is as a metric of time in seconds is a very weird idea. So instead, we can kind of have an abstraction of efficiency. And it's kind of a fundamental motivation. This kind of abstraction of efficiency is a fundamental motivation for data structures, and algorithms, and theoretical computer science in general. Okay, so what do I mean? So let's start with an algorithm. So an algorithm, as you might know, an algorithm is essentially a finite set of steps that solves a particular problem. Okay, that's all cool. So what is efficiency then? So efficiency, this is in an abstract sense, is the approximate number of operations that an algorithm needs to solve a problem for a particular set of inputs. For a particular set of inputs. So what do I mean by this? Essentially, if I have one input for our drought problem, it's going to take one step to solve. If I have 1,000 inputs, it's going to take 1,000 steps to solve. But there are some programs for which this is not the case. For example, let's say I wanted to list all of the permutations of a set of numbers. So for example, if I had the numbers 1, 2, 3, 4, I could list, or 1, 2, 3 maybe, I could list all the different permutations of it. For example, 1, 2, 3, 3, 2, 1, 2, 1, 3, 1, 3, 2, etc. And there's six different permutations of these three numbers. Okay? But if I had 20 numbers, there wouldn't be 6 permutations of 20 numbers. There would be much larger than 20 permutations of 20 numbers. In fact, the number is 20 factorial, which is like 20 times 19 times 18 all the way until 1. And this is a huge number. So in this case, the amount of steps you need to solve the problem, or in this case to list each of these combinations, is much larger than the number of inputs. Whereas for our drought problem, it was a lot easier. For each input, we needed just one extra processing step simply because we just needed one more iteration through the loop. So the abstract measure of efficiency, called computational complexity, is essentially the approximate number of operations an algorithm needs to solve a particular problem as a function of the number of inputs. So that's a very important detail, as a function of the number of inputs. So in this case, with this linear search, this function varies linearly. So if I have 1,000 inputs, it's going to take me some constant times 1,000 number of steps to solve, right? Maybe it'll take 2,000 or 3,000, but it's not going to take something like 1,000 squared or 1,000 factorial or something weird, right? Whereas, for example, if I wanted to go through every element in a 2D array, well, there's n squared elements in an n by n array, so the amount of time it takes to go through an n by n array is approximately proportional to n squared, not n. All right, here's another interesting example. Okay, let's do another example just to kind of run the point home. Okay, here are two pieces of code, and I want you to kind of analyze them or try and understand what they do. So here's the first piece of code. Count equals 10 to the power of 5. We have an array called nums, and for I in range count, we want to append, and then we want to reverse. Okay. So what does this do? Essentially, it appends all of the numbers from 1 to 100,000 in an array, reverses it, and then I guess we can print nums now. Okay? Print nums. I'm not going to print everything out because it's 100,000 elements long. But you get the gist. So this is the first piece of code. Here's another piece of code. Okay? The other piece of code is count equals 10 to the power of 5. For I in range count, oh sorry, I'll make nums be separate, nums be an empty list, nums dot insert 0 I. Okay, so what is this doing? So what this is doing is inserting elements at a particular position and doing something similar. Okay? So which one is more costly? It turns out the insertion is much more costly. And do you know why? It's because when you go through an array and you try and insert something in the middle of the array or in the beginning of an array, essentially you have to move all of the other elements out of position. And that's really bad for your time complexity, because for every step it's taking n more steps to be able to solve the problem. So this is what we call an n squared algorithm, which means the processing time, or number of operations to process an input, is proportional to the square of the number of inputs, whereas this is linear, because all we're doing is adding to the end. This is a linear time, or n algorithm. And what computer scientists do is they denote this by O of n. Essentially what that means is it stands for order of n, meaning some constant times n. Some constant times n. And they call this order of n squared, meaning some constant times n squared. So obviously you might be doing processing inside this loop. You might be doing some operations, some arithmetic operations. What do we count as constant, right? That's a very interesting question. Usually we count arithmetic comparisons, we count list appends and things like that, if statements, all these sorts of things as kind of constant time operations. Because a computer can compare two numbers easily, it can do arithmetic easily, it can append something in an empty memory location, usually pretty easily unless it has to shift other elements to do so. So these are the easy things that computers can do. So why is this kind of abstract measure of efficiency, which is essentially trying to compare things as a function of the number of operations as a function of the number of inputs, better than simply measuring something in seconds? Well, it turns out the first reason is that you can compare different algorithms on different pieces of hardware. So, for example, your version of the drought problem in C++ may take 0.004 seconds, mine might take 0.01 seconds, and you might say your program is faster than mine. But if I write my program on your hardware, they'll run at the same speed. Okay? They'll take the same amount of time. So is your program really faster? So what we're trying to compare is not the program itself, but the algorithm, the underlying idea, the abstraction of the particular problem. So that's why this kind of abstract measure of efficiency called computational complexity is much more powerful than simply measuring things in seconds. The second reason is that computer scientists realized that they kind of had a way of comparing different ideas across hardware. They didn't need to even look at seconds anymore. They didn't even need to look at hardware anymore. They knew that if I can make the abstract idea this efficient, then I can use hardware to improve as much as I need usually, or as much as I can improve. And the reason why we use the abstract measure of efficiency in practice rather than necessarily always measuring everything in seconds is because faster algorithms generate much better speed-ups than faster hardware. For example, if I wrote this problem, if I wrote a better algorithm for this problem, maybe I managed to sort my data, maybe I managed to do something to get the time down, or maybe I had a running count of the rainfalls, and whenever somebody told me another rainfall, all I had to do was add something, so I would take less time on the fly. So it's something like that. Maybe I did the whole process online, or on the fly. These sorts of things can have a much better impact than simply transferring the hardware, or the hardware that the program runs on, from my laptop to a supercomputer. So algorithm speedups are much better than hardware speedups. And they're much more consequential. And they also start to matter more and more as the amount of data you need to deal with increases. I'll talk more about this in the next seminar. But now we kind of have a little bit of an idea of efficiency. I'm going to end with essentially what assumptions we have when we apply this abstract measure of computational complexity or algorithm efficiency. So first of all, we're assuming that we don't have any access to concurrent execution. So we can't run things on multiple threads. We can't somehow do some distributed magic that will allow part of our program to be running with another thread and one part, and the second part of our program to be running with a different thread and something like that. We can't do that. The machine simply executes one instruction after the other. Okay?
We also assume that standard basic operations like arithmetic, comparisons, memory access all take constant time. And there are no more complicated basic operations. So for example, sorting is not a basic operation simply because it's made up of comparisons, right? Most sorting algorithms are just made up of comparing one thing to another over and over again until essentially you get the result you need. And swapping. So swapping is one basic operation. The comparisons are a basic operation, but the actual sorting is not a basic operation. It's a combination of basic operations. And also one computer word, or the size of a value that we can work with in constant time, is not unlimited, but it's big enough to address all the memory locations used to represent our problem. So essentially, the variable allocation takes a constant amount of time. So we can allocate things pretty easily without having to use too much memory that it takes a lot of time. So under all of these assumptions, we can apply this kind of abstract measure of computational efficiency, and we'll see that this has a lot of relevance. It's probably the most important concept in all of programming contests. And it's used in order to devise and compare algorithms, and eventually to devise faster, more insightful, clearer, and just better algorithms in general. So we're going to stop here. I hope you guys enjoyed this first workshop on programming contests. And I think that we're going to continue this in the weeks to come. And I'm hoping we can have a programming contest in week 7 or the mid-semester break. We'll see how that goes. And I think this is a good start of things to come. Please let me know if the format worked well on Twitch with the streaming. The video will also be uploaded to YouTube. It'll be put on the Syncs Discord. The programs can be put on the Syncs Discord and so forth. So yeah, please let me know if you have any problems, if there are any issues, or if you need any more resources. I'm going to stop the stream here. Thanks very much for coming and participating. Have a great day.